Good afternoon, everyone. I'm Andy Brown, Director of Research at ECMWF, and it's my pleasure this afternoon to tell you about Cycle 46R1 that we're really quite excited about. Of course, I'm reporting on the efforts of many people from right across ECMWF, far too many to mention. Just particularly mention Phil Brown and Mikhail Diamantakis, who provided the scientific coordination and pulled together a lot of the material. But as I said, the work's come from very many people. This webinar will focus on the science of the cycle, and slides and a recording will be made available later. There will be a separate webinar in May where we'll get more into the details of the implementation, availability of test data, new products. So I hope that will be of interest to you nearer the time. This is a really important cycle for us because it's an opportunity to bring together lots of exciting science. Before we moved to Bologna, we wanted to really pull together our science, get a strong cycle together. And I think we've done that. In addition to the contributions themselves, we worked really hard on the process for pulling the cycle together so we can systematically bring together all the different contributions. And so that's led to a really strong focus on the Ensemble system right through our testing, as well as the high-res system. We've also had an eye right through on the performance across timescales, consistent with our seamless strategy, so looking at the medium range forecast, the extended range, and indeed testing it on seasonal timescales. So I'm really pleased to share this with you, and I hope it's of interest. So I'm going to talk through first the data assimilation and observation highlights, then some of the model developments, and then finish with just some overall how it all comes together and what it looks like. So here's a list of the main developments on data assimilation and observations. The things in blue are some of the big ticket items that I'm going to say more about in later slides. So continuous data assimilation, changes to the ensemble of data assimilations, changes to satellite data, and the coupled assimilation. But I'll just very briefly touch on one or two of the items in black, which I'm not otherwise going to say more on. So there's been major developments to the soil moisture analysis, where we're now taking more information out of the ensemble of data assimilations. That makes the system much more efficient, saves us computational power, and therefore lets us do more exciting science. Also have SMOS data assimilated for the first time, so that's really good. And we're always increasing the number of different observations we use. So in this cycle, there'll be new microwave channels, for example, the 150, 166 gigahertz channels from SSMIS. So big list of contributions as ever. But going through some of the big ticket items, so this first one is what we call continuous data assimilation. So this top line here is showing the current situation. So we wait till a certain time for all the observations to come in, and then the data assimilation does 3 minimizations, so 3 iterations of data assimilation, and each of these takes 10 minutes or so. So the first thing we can do is think, well, this is an iterative process. After we've done the first of these iterations, why not have 10 minutes more observations? We've got more up-to-date information to put into the system. We can get a better analysis and better forecasts. Then after we do the second minimization, let's let in more observations again. So we've immediately gained 20 more minutes of observations into our system to make the forecast better. But it's actually more significant than that, because once we've done that, we're now saying that the time we start the data assimilation here is decoupled from the latest observations we're using. And that means we could start data assimilation earlier. So we can now afford to do more expensive and, more importantly, more accurate data assimilation without losing observations. And so we take advantage of that. We're going to change how long we do the assimilation. Instead of over a 6-hour window, we'll do it over an 8-hour window. And instead of having 3 minimizations as we have now, we'll have 4 minimizations. So we're using more observations, we're using more accurate data assimilation scheme without affecting the time the forecast is available to users. So this just summarizes that. The picture at the bottom left is just showing the extra observations that end up getting used in a given cycle. So lots more observational input going into the analysis, a more accurate analysis, better forecasts. This is really exciting at 46R1, but also this decoupling of the observation time from the start time data assimilation opens up further avenues where we believe we'll be able to take even further advantage in later cycles. So this is just showing some sample results looking at the accuracy of the wind forecast from the system. So each of the panels looking at different time ranges, and blue and green colours mean we're doing well here. If we're getting yellows and reds, we're making the forecast worse. So these first 4 panels are just looking at the first stage of this process where we've just let in the 20 minutes of extra observations. And you get a mild improvement, mainly the blue turquoise type colours. We then, because of this decoupling, can then, instead of doing a 6-hour window for data assimilation, we do the 8-hour window. And on top of the previous one, we now get to this situation. So you see the colours are getting bluer, stronger colours. We're getting further benefits from having done that. And if I take the last step, and instead of doing these 3 iterations, I do 4, I get to these panels. So really very significant improvements, all latitudes, all heights. So a very significant advance. The next major innovation here is we run an ensemble of data assimilations. So we don't just do the data assimilation once, we currently do it 25 times. And there's 2 ways we use that. One is we take the spread of that to tell us what's the uncertainty in the background for the 4D variational assimilation. And the second way we use it is part of initializing the ensemble members. And at the moment, we only have 25 members of the ensemble data simulations. A cycle 46R1 will change to having 50. And that gives us 2 benefits. An improved 4D VAR analysis for the high-res forecast, more accurate high-res forecasts, and also an improved ensemble initialization. Because at the moment, we only have 25 members of this ensemble of data simulations, but we have 50 forecast ensemble members to initialize. And so we have to use each member twice with a plus-minus symmetry. So I'll show a couple of results from that in a minute, but that work has only been made possible by a huge amount of work optimizing the system, because obviously running 50 members instead of 25 uses more computer power. So it's needed a lot of efficiency work in order to let us be able to afford to do that. So I'm not going to go through all the details, but lots of strands of work finding where can we make the existing science cheaper on the computer so that we can afford to do better science and get the better forecasts. So this is just illustrating in terms of the ensemble forecast, so the 50 members of the medium range ensemble. The top line is the status quo as we are at the moment. So this is the first member of the ensemble, has some perturbations from the ensemble of data assimilation. See the blues and reds, positives and negatives. And then member 2, we've just flipped that on its head. So the blues become red and the reds become blue. Similarly, members 3 and 4 are mirror images of each other, right up to members 49 and 50. If I then go to the new situation where we have 50 members, we have 50 genuinely independent ensemble members. And so that's good for our ensemble system. And if I look at the impact, so this is an ensemble scorecard, so far too many measures to look at in detail, but here we have Northern Hemisphere, Southern Hemisphere, and tropics, a range of different measures, geopotential, height, temperature, some against analysis, some against observations. And on this scorecard, greens are good and reds would be degradation. And you can see it's very largely green. That's both because it's getting a better analysis from the high res and then getting better perturbations from the ensemble of data simulations. Just to give you a sense of scale, this is looking at the 500 hectopascal height in the Northern Hemisphere. And you can see we're getting improvements of certainly order of percent in the Northern Hemisphere and similarly in the Southern Hemisphere. So significant improvement from that upgrade and consistent with the seamless strategy again. Traditionally, over many cycles, a lot of improvement in the forecast continues to come from using existing satellite observations better. It's an ongoing effort to extract more and more value out of the existing satellite data. This is one example, and I'm not going to go into all of the details, but introducing inter-channel error correlations on the microwave sounder on SUAMI NPP satellite, the American satellite. This is something we've already implemented on some of the European satellites. The first time we're doing it on the American one. And if you look at the panel down here, this is looking, after we do that, how well does the first guess, the very short range forecast that goes into the analysis, fit independent observations, in this case looking at radiosondes. And if we're looking to the left of the 100 line, it means that after we treat the satellite data better, we're doing better. And you can see consistently the new system fits the independent radius on data better, which gives us confidence we're doing the right thing. So that's the better analysis. And then if we look into what does that do to the forecasts, looking at the northern hemisphere at the top, southern hemisphere at the bottom, here looking at the vector wind scores, and see we're getting another 0.5% improvement in both hemispheres out of this change. Another change, satellite usage. This is looking at the geostationary. So that previous work was the low Earth orbiters. Now we're going right up to the geostationary satellites. 3 changes in the usage here. The first one, rather like we're just talking about on the microwave sounders, is introducing interchannel error correlations inside the data assimilation. The second innovation is introducing slant path radiative transfer, particularly when we're using these satellites to look at high zenith angles, so quite slant paths. The path through the atmosphere can actually become quite long, such that it passes through lots of different columns of the IFS integrated forecasting system. And up to now, we've just taken one representative column, but now we're saying, actually, we're passing through enough columns, we should take information from the most relevant column at each height. And one of the things that does is it lets us extend the usage of this data to higher zenith angles. This plot on the left is showing the geostationary data we're currently using. So if we concentrate here, Meteosat 10, the green circle, that's what we're currently using with the current operational system. You see, the top of the data, we're probably just about getting up to the UK, for example. When we introduce these changes, we can start using, instead of up to 60 degrees, we can go up to more than 70 degrees zenith angle. So that gets us to this picture, and see the outer range of the data we're using from these geostationary satellites is now up approaching Iceland. So we're bringing in more data in the North Atlantic, and we can show that and gives us some improvements in the performance, particularly the jets. The last topic I wanted to mention on the data assimilation and observation side was at the last cycle, 45R1, that we introduced last June. We were really quite excited by that one, because the first time all our forecast systems became coupled to an ocean. So it wasn't just, you just used an atmosphere for forecasting, both from medium range to extended range to the seasonal forecast. We were coupled to an ocean in the forecast model, which I think was quite an innovation. But at the time we did that, we were still, for the data assimilation, using the previous sea surface temperature product. So what we were doing for data assimilation and what we were then doing when we did the forecast system wasn't quite consistent with each other. So what we're doing here is switching so that the atmospheric data assimilation for the first time now sees the same sea surface temperature that the forecast model is going to start from. So it's an exact consistency match. That gives us some improvements in scores, particularly near the surface and in the tropics, where this has the main impact. And so, as well as being valuable in its own right, it's another incremental step on our sort of strategic path towards more coupled Earth system assimilation. Changing tack now to the changes to the model. As before, there's a number of items listed in blue that I'm going to talk about in more detail, and then a long list of further details, and you'd find more information on all of this on the web, and as I say, the slides will be posted separately. Anyway, but just to mention, maybe one of the ones I'm not going to labour, the adjustment of the wet skin tile conductivity. That's in the land surface scheme, the coupling of the land to the atmosphere. This change, it's not something that affects the area average forecast scores very much, but we have had a limited number of instances where there can be a small instability in the current system, where the temperature oscillates not realistically, and that can result in a rare number of occasions in unrealistic maximum temperatures. And so we had some user feedback on that, and this change very largely addresses that problem. So not something that affects the scores, but something that, in terms of really local forecasts, I think is worth mentioning. So in terms of some of the major model contributions, so the first one, the radiation scheme in the model. Currently, in the high-res system, we run the radiation scheme every hour. But in the Ensemble system, we only run the radiation scheme every 3 hours. And that's purely a computational cost argument. We've always known we'd like to do the radiation more accurately. Clouds change, the weather changes, we want that more accurate radiation, but we haven't been able to afford it. So an innovation over a couple of years, developing a new radiation scheme, more modular, more efficient. We introduced this radiation scheme a cycle or two ago, but now that means because it's more efficient, we have the slack in the system to be able to afford to do what we've always wanted to do. So we're now running, well, from 46R1, we'll be running every hour the radiation instead of every 3 hours. So here's a scorecard as I showed you before, now updated to the new colour system where blue is good and red is bad, but I think an impressively blue scorecard. And if I just hone in, here's 2 meter temperature in the tropics, and specifically 2 meter temperature over Europe, looking at the change in the scores, and see, if we look at, say, 144 hours, getting maybe 2.5% in the tropics, and probably 1.5% in Europe. So improving near surface temperature, something that's clearly important to many of our users. So definitely something we've wanted to do. On a slightly different topic, ECMWF, on behalf of the European Union, runs the Copernicus atmosphere monitoring service. And so that does detailed forecasts of aerosols and atmospheric composition. And we've been gradually moving to take more advantage of that in the main forecasting system. So this, at the previous cycle, we started taking the climatology of aerosols from the CAMS Copernicus system. And this is updating that to use a full 3D climatology based on that information. So something we couldn't do if we didn't have the Copernicus service, making what we're doing in the IFS meteorological forecasting system really take advantage of what we have from CAMS. It has mildly positive impacts on the scores, but I think puts us in a better place in terms of future development path. And so we'll be, for example, testing if we start introducing more prognostic aerosols, can we show benefits on the medium range forecast? Snow scheme improvements. This is another of the changes, really motivated by local forecasting problems. You wouldn't see the effects of the change here in any scores averaged over Europe or over a season. But we'd had, again, rare examples of where we could get unphysical accumulation of snow if in reality it snowed and then it started raining. This is one example from Bulgaria, a single case study, but I think it's illustrative. So in reality, it snowed for a day or two here, and then it turned to rain. And this purple line is what the current forecasting system did. So it realistically snowed, and this is the snow water equivalent. So we had snow on the ground, and then when it started raining, this rain was all effectively freezing in the snowpack, so the snow depth was going up. Whereas in reality, it wasn't. The snow depth should have been going down. And so changes to the way existing snow intercepts rain falling on it, we've moved to this green line, which is more realistic. So you wouldn't see this effect very often, but in this particular meteorological conditions, that will lead to improvements in the forecast of snow on the ground. Another area that we continually work on is the tangent linear and adjoint model. So this is right in the heart of the 4D VAR system, where we have simplified physics, a simplified model that we're using within the data assimilation system. And making this more accurate is important for the accuracy of the analysis and hence for the forecast. It can be important for the robustness of the system, particularly as we go to higher resolution. And here, in this cycle, we've made a couple of changes. One to the accuracy of the system over the pole, another one to change to the convection scheme. And what we're looking for here is to show that this new linear scheme is more consistent with the non-linear scheme. And if we're in the blue colours, it's saying that we've managed to make the linear scheme now more consistent with a full scheme than it used to be. And you can see very largely a blue pattern. And this is just showing percentage improvements. And so we're a percent or two closer. And so that helps the accuracy of the analysis, and then hence helps the accuracy of the forecasts. Last thing on the physics, on the wave physics. For a number of years, we've tended to have slightly too much swell in the tropics, not enough waves in the stormy and windy areas. So this is looking at significant wave height from the system. And so the blue colours are showing the errors in the tropics compared to the red in the stormy, windy areas. Now, Métier France did a lot of work building on the work of Ardouin et al., changing the wave physics. And we've taken on what Métier France did and incorporated it in our system. And so looking at the changes we produce. And so we're increasing the amount of waves in the extratropics, and we're decreasing the waves in the tropics, which is in antiphase with the errors that we had. So that's sort of well-founded scientific work, taken on by Métier France, taken on in turn by us, improving the quality of the wave forecasts. And if we look at what that does, the thing to focus on here is the green lines. So this is looking at significant wave height errors, so percentage changes in actually the significant wave height. So here we have the southern hemisphere, here we have the tropics, and here we have the northern hemisphere. Below the zero line is good. So you'll see, certainly out to day 6 or 7, we've reduced the root mean square error, tropics, northern hemisphere. Does look like we've got a slight increase in errors at long range, but what's the cause there is that we've actually made the wave model more active. In this new system, that there are more waves than there were before, and that's actually a good thing. This is just looking at the standard deviation of significant wave heights, comparing the new wave physics to the old wave physics. So here's buoy data. We want the model to lie up this diagonal. The blue is where we are with the current system, and the red is where we are with the new system. So we more accurately have a more active system. You do get penalized for that at the root mean square error, but the anomaly correlation also remains positive. So we think this is a well-founded package of changes which is improving the quality of the wave forecasts. So that I've run through very briefly some of the main contributions. So obviously we've done a lot of work starting testing these individually, then packaging them together, higher resolution, fuller and fuller tests. So I'm just going to try and give you a sense of where we are with this testing. So this is looking at one of the headline scores from the high-res system, just looking at 500 hectopascal height. So southern hemisphere on the left, day 0 to day 10, northern hemisphere on the right. The zero line is where we are now. The black line is where we get to if we package together the data assimilation and observation changes, but not yet the continuous DA and the ensemble of data assimilations. So we're getting improvements of a % or 2. If I go to the red line, that's bringing in the physics, and then beyond that we bring in the waves. And so the combined effect of all of them, a couple of % in the southern hemisphere, percent and a bit in the northern hemisphere. But that's before we bring in the continuous DA and the ensemble of data assimilations. So if we then do that as well, so this is now full resolution testing. Again, 0 is the baseline, negative numbers are good. And you can see in the southern hemisphere, we're right out to day 10, more than 2% improvement. In the northern hemisphere, depending exactly what time range you look like, but 3% or so throughout the time range. And if we look at the full scorecard from the ensembles, this is everything packaged together as before. Blue is good, red would be a degradation. Various scores against analysis in the top half, against observations in the bottom half. I think this is one of the bluest scorecards I've ever seen, so I think we're really quite pleased that we have a strong cycle here. And just to give you a sense of sort of cross sections of that, so this is looking at temperature, this is looking at humidity, different time ranges. I don't know, if we look at 168 hours, blue colours are good, different latitudes here, height here, and see, particularly in the northern and southern hemispheres away from the tropics, very strong and consistent signal everywhere, more neutral in the tropics. And yeah, across lots of different measures, it seems to be consistently strong. And well, here's just two other measures. So geopotential height, vector winds, again, blue colours, good. So different time ranges, different geographies, I think a strong cycle. Last thing I wanted to mention was we run reforecasts, particularly for the Ensemble system. If you want to calibrate real-time forecasts, you need to know the characteristics of the system. So we run those reforecasts, which are used operationally. You can use them to assess the skill of the forecast, to calibrate the extended range products, and to produce the extreme forecast index. And obviously we need to initialize those forecasts from somewhere. And up to now, we initialize those forecasts with ERA interim, the ECMWF reanalysis. But again, and this is another example of sort of leveraging the efforts of Copernicus. So the Copernicus Climate Change Service, run by ECMWF, has recently produced the new ERA 5 reanalysis. And yeah, we believe that to be a huge step forward compared to ERA interim. 10 years or more of science developments, a higher resolution reanalysis. We believe it to be a much better reanalysis. So we want to move to initializing these reforecasts with ERA 5, the new more accurate reanalysis, rather than what we've been using up to now, ERA interim. But of course, while we expect that will be a good thing, we need to check before making such a change that it is. So this is looking at the extended range forecasts. It's a different sort of scorecard, but here's various measures, T2 meter temperature, surface temperature, 200 hectopascal winds, 850 temperatures, so a range of different meteorological variables. Here's in the Northern Hemisphere, week 1, week 2, week 3, week 4, and in the tropics, week 1, week 2, week 3, week 4. And on this scorecard, blue is good, dark blues are statistically significant, and the bigger the blue circles, the better it is. To give you a scale, this is a 1% improvement, this circle. So I think that's pretty strong signal that using this more accurate reanalysis does translate through into the more accurate reforecasts. And it also lets us simplify our suites. So I think that's all I had to say. The implementation is planned for June. As I said at the start, there'll be further webinars in May. They'll focus more on the final verification scores from the final e-suite, technical access to the test data, and on where there are new parameters, new products available for users. So initial test data will become available soon, and really just a plea, do watch the implementation page. There's a link here, so as progress is made or as news evolves, there'll be more there. So I hope that's been of interest. I hope it's come across that I'm quite excited by this cycle. And if there are any questions, I'm sure my colleagues will read them to me.
So Todd Kimberlane is asking, have you seen improvement in the model's ability to predict warm season convective rains?
So in case people didn't hear the question, I was asked, have we seen the ability of the model to check warm season convective rains?
Have you seen improvement in the model's ability to predict those warm season convective rains? I
think that's something I will have to look up offline. I wouldn't like to speculate, but I would hope amongst the package of improvements, and given how widespread the improvements are, I would be reasonably optimistic, but I wouldn't want to promise without going away and checking.
No, not at the moment.
Okay.
Nobody's typing anything?
Yeah, okay. Well, if there's no further questions, thank you very much. No, I'm being waved at.
Jason Lin is typing.
Yeah.
So let's wait for him to finish. And Brian Etherton is also typing a question.
Okay.
So Jason is asking, any additional comments on the two MT forecast issues over a strong soil moisture and or a snow cover items?
So, yeah, I'm not quite following the question, but in terms of 2 meter temperatures, I think we certainly know that the move to hourly radiation. Sorry, I'm just trying to read the question. So, strong soil moisture or snow cover anomalies. So, in general terms, the radiation change to the hourly radiation in the ensemble, in a widespread sense, improves the 2 meter temperature. I think the improvements to the soil moisture analysis, the coupling to the EDA, give some improvements in near surface temperature. In terms of over snow, I think it will be a future cycle. One of the things we're very actively working on is a multi-layer snow scheme. At the moment, we only have a single layer snow scheme, and particularly at high latitudes where you can get the extreme temperature gradients through the snowpack, it's very, very difficult for a one-layer snow scheme to capture that. So I think the improvements over snow will come in a future cycle because some of the early results using a multi-layer snow scheme are looking quite promising, but not yet ready for implementation.
Can you see the next question from Brian?
Yeah. Any early indicators on tropical cyclone prediction with 46R1, either track or intensity? That's quite timely because I saw some first results this afternoon. So I think in terms of track, it looks positive. Not dramatically so, but there are improvements in track. I think it's too early to comment on intensity, but yeah, we're actively looking at the tropical cyclone scores just now.
Okay. Jason is typing. And so is Todd. So you have a question now from Jason?
Yeah. Oh, any basin differences with those tropical cyclone comments? I wouldn't be able to comment. I mean, of course, we're looking at all the basins. I literally looked at the aggregated results about half an hour before coming here. Whether the sampling is large enough to be able to safely make comments at a basin level or not yet, I don't know. But I think we're pleased to see, at least across a multiple basin result, that the headline result is in the right direction.
Okay. And Todd just added another question.
Yeah. Okay. I suggest actually, given this is so new, I'm not going to try and speculate further on tropical cyclone scores, but as I said, there'll be a further webinar in May, which the focus will be much more on the final system with the full suite of verification, and we can certainly make sure there's a sort of a strong focus on the tropical cyclone results as part of that.
Jason is typing.
Okay, thanks, Todd. So a question from Jason, conclusions of the early test about treatment of MJO and other convective forcing. I'm not going to be able to answer that in detail. Of course, it's something we look at. The extended range performance, which obviously MJO is a big part of, looks good in this cycle. But in terms of really analysing in detail those changes, we have further work to do. I'm writing all of these down to remember to look up more.
Is there another question from... No.
Nope.
Brian, there's a comment.
Yeah. Okay.
That should be it.
Oh, hang on, Brian's typing again. Okay. Thanks, Brian. If there's no more questions from everyone, well, thank you very much for your attention, and thank you.